Now let's prove some the properties of the probability law P using three axioms. Again, remember that we have a axiom 1, non-negativity. The second axiom is normalization, and third axiom is finite additivity. So let me give you some time to think about this problem of proving the first thing and the second thing and the third thing only using the three axioms. So please pause the video and then try to prove these three things. Okay. First is that the for any event, the probability should be less than or equal to 1. Okay, it looks too natural, but we need to prove using these three axioms. The first, from the second axiom, the probability of the whole sample space is equal to 1. Okay. Now, the sample space omega is the union of two disjoint set A and A complement. This comes from the set theory. Now from the third axiom, which is the finite additivity, the probability of A union A complement is equal to the probability of A and probability of A complement. And that means the probability A is equal to the 1 minus probability of A complement, because this is 1 and this part. Good. And the next step is that from the axiom 1, probability of any event should be positive. And that's why this probability of A should be equal to less than or equal to 1. So again, the probability A is less than or equal to 1 looks too natural. But that's what something we need to prove using the three axioms. What about the second one? The probability of the empty set is 0. So first thing is that the probability of omega union empty set is equal to the summation of the probability of the samples, the omega plus the probability of the empty set. And that's coming from the finite additivity, third axiom. And that is equal to the 1 plus probability of empty set. That means that this probability should be equal to 0. That's coming from the first thing. Because from the first property, all the probability should be less than or equal to 1. So that's why the probability of the empty set should be equal to 0. The third thing is that if the A is a subset of the B, then its probability should be less than or equal to the probability of B. From the finite additivity third axiom, the probability B is equal to the probability A plus probability B set minus A, right? A and B set minus, that's disjoint. Okay. Now from the first axiom, this guy probability should be positive. So we have this thing. And there are many other things that you can prove from these third axioms, and then we actually building up all the properties of the probability law that probably you think are natural. Okay. So general probability calculation steps consist of the following 4 steps, right? First is that we need to specify the sample space. For example, in a tossing a bias, for example, coin, here the bias means that the probability of head and probability tail does not have to be half. It can be something else. So if we specify the sample space, then the omega is h and t. And as a second step, we need to specify the probability law. What is the probability law? Assigning some numbers to each event. Here in this case, because we're talking about discrete case in this example, it's enough to assign the numbers each outcome. And how can we specify probability low? Well, that's coming from some model or my belief or some data or some expert opinion. Okay. Now identify an event of interest that you want to look at. Here in this case, for example, okay, I'm interested in the probability of hat or probability tail. It's a simple. For example, if you roll a dice, then you might be interested in what is the probability of having like even numbers or odd numbers. So if you identified an event of interest, then now you're good to go and calculate the probability. So those are the probability calculation steps. So let me give you another example. The discrete case again, here in this case, the sample space is that of the just natural numbers like 1, 2, 3, 4, but it's an infinite. Okay, so 1, 2, 3, 4, 5, 6, and then so on. And the probability low that I have, which probably somebody gave me, is the probability of each number is that 1 over 2 to the n. So probability of 1 is 1 over 2, 2 is 1 over 4, and so on. First, is the above probability low? This thing is the legitimate? Well, it seems okay. Why is that? Because first, I need to check that the summation of all probability should be equal to 1. And it turns out that it's true because the probability of the whole thing is 1 over 2 and 1 over 2 to the 2 and so on. And we know how to calculate this. So it's a 1 over 2 divided by 1 minus 1 over 2. That is equal to 1. I'm interested in the probability of the even numbers. And that is probability of 2, 4, 6, and so on. And that is equal to the 1 over 2 to the 2, 1 over 2 to the 4, 1 over 2 to the 6, and so on. And if you calculate this thing in the 1 minus right, the summation of infinite series, so it should be 1 over 3. Okay, is the above right? Just think about it. Is this right or wrong? The answer is wrong. Why the answer is wrong? Because we just have the 3 axioms where the third axiom is the finite additivity. It does not define any rule of making the summation of the infinite series. Here at the moment, we don't know whether our probability low allow this infinite series of the summations. Again, we are in the middle of the building up of this probability low. Okay, so don't use your common sense. Here's no common sense. We're building up this P and the capability that the only P has the summation of the finite number of disjoint event. But here in this case, we are dealing with an infinite number of the disjoint event. So we are not able to do that. Which means that we need to change our axioms or extend our axioms a little bit. So this was the probability axiom version 1. Where the main part that needs to be changed is this part. So how should we change this thing? It's a countable additivity. The countable additivity means that if the infinite series like A1 and A2 and A3 and dot 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 is an infinite sequence of the disjoint events, then it's possible that the probability of those union of those infinite sequence of this disjoint event is the summation of the probability A1 and probability A2 and so on. And obviously this countable editability includes finite editability as a special case, right? Because up to the end point, we have some meaningful events, but after that, it's okay that we have an empty event. So it includes the finite editability as a special case. So essentially what we're doing is that we're extending the probability axiom version 1 into the version 2, so that this kind of countable editability is satisfied. You should not ask why this is true, because this is what's axiom. Axiom is something that we don't need to prove, and it's a starting point of some whole theory, whole area of the theory, which is the probability in this case. And we believe that this is true. That's why we don't need to prove. But we're going to prove other things using these 3 axioms. That's what this axiom means, right? Okay. So, all right, we're so far we're done with talking about these probability axioms. Just a little bit of different story of the probability theory. There are different view or interpretations of understanding the probability theory. So, first interpretation is something kind of narrow view. That's a branch of math. So, what is the math again? We first start from the axioms, and then we build up a lot of theorems which tells us the nature of those structure of some area. Here in this case, probability theory. So that's why we set up some 3 axioms, and all of the other things that we're gonna talk about is what are the theorems that can be proved using those axioms. And obviously mathematicians work very hard to find the smallest set of the necessary axioms. We don't need to include everything. We need to include just the smallest set of the necessary axioms. It's like atoms in physics. And that's what the mathematics is all about, right? And that's one view. And another view is the frequency interpretation, which means that we understand uncertain situations as a fraction of successes out of many experiments. For example, if somebody says that, okay, when we toss a coin, the probability of the head is 1/2. Why is that? I mean, how can we understand that thing? That can be understood as okay, if we toss a coin infinite number, like 1,000 times, then roughly the 500 times we get a head. That's why the probability of head is 1/2. That's an understanding of uncertain situations as a frequencies of the successes. That's another interpretation of the probability theory. But in the real world, there are many uncertain situations that cannot be repeated. For example, there are some politicians, and some people will ask the question, what is the probability that he is re-elected? Like he's the president of some nations, and he's gonna run for the president in the next term. And some people ask the question, well, what is the probability that he is re-elected? Then obviously we cannot do this kind of experiment like 1,000 times, right? Here in this case, well, if somebody says, okay, well, what I'm thinking is that the probability he's re-elected is like 0.7. And that is the belief. Well, the belief can be, it's not something right or wrong, it's just a belief, subjective belief. That can be coming from some expert, or that can be coming from some of your experience. That's how we understand the probability. That's what I'm talking about. So in this case, the probability can be thought of as some kind of subjective beliefs. There are many 3 things. We're not saying that, well, which is right or which is wrong. This is how we understand the probability. But anyway, we believe that the probabilistic reasoning of some uncertain situation is very helpful to understand the world with many uncertain situations. And we believe that the usefulness of this probability thing to do some other things. And that's what we're going to do throughout this course during the entire semester. Okay? All right. Thank you.